what we're going to do today is we are going to discuss acceleration. What is acceleration? What's the relationship between acceleration and motion? How does it relate to velocity? How does it relate to position? So let's start off. Thank goodness the universe allows us to move. Otherwise, it would be a very, very boring universe. Okay, it sounds kind of silly, but it is. The amazing part isn't that the universe isn't that we can understand the rules of the universe. The amazing part is that the universe has rules in the first place. So anyway, where am I going with this? We know that the change in position over time is how we're going to define velocity. Okay? So velocity is change in position over time. Thank goodness, again, the universe allows us to change the velocity. All you got to do is take a look at any race. In any race, the racers always start at 0 and then they go up to some kind of speed. So the velocity can change as well. We're going to call that change in velocity over time the acceleration. Right? So our definition of average acceleration is the change in velocity over a time interval. Mathematically, we would write it as a bar equals delta v over delta t, or vf minus vi divided by tf minus ti, where vf is the final velocity, vi is the initial velocity, and tf minus ti is the time interval. So if you're running a stopwatch, it's what you would read on the stopwatch. Otherwise, it's the difference between final time and initial time. All good there? Everything make sense? Or at least you're following along with it? Okay, now comes my test. Okay, my test is this. A tennis ball is traveling at 22 meters per second and hits a wall. If it is in contact with the wall for 0.02 seconds, 2/100ths of a second, and has a speed of 18 meters per second when it bounces off, what is the ball's average acceleration? I would like you guys to work together as groups. You've got your whiteboards available. You can go ahead and discuss that amongst yourselves and see if you can calculate the acceleration. So, I'm looking around, and most of you have an answer in the 200 meter per second squared range. And most of you would be wrong. Okay. Now, there is a way to solve this that's really, really easy. What I mean to say is this. You guys know how to solve it, and the method you're using to solve it is correct, except you're making a fundamental mistake. So, how do we go about that? I gave you a problem-solving technique last week. You guys remember that? Step number 1 after you read the question is to draw a picture. So let's go ahead and draw the picture. There's my before and after. In the before, the ball is going into the wall with a certain velocity. In the after, the ball is coming out of the wall with a certain velocity. Right away, some of you, the light bulbs should start to come on. That's okay. It may take a little bit more before they get to that. But next step, we label the diagrams. I have VI is going to be the top ball. There's the arrow representing VI going into the wall. And then there's the arrow for VF representing the velocity coming out of the wall. Next thing I'm going to do is I'm going to get my table of knowns and unknowns, but I'm also going to establish directions. Which direction is positive and which direction is negative. I'm going to define going into the wall as positive. That means coming off of the wall is negative. That means VI is a positive velocity and VF is a negative velocity. And so when I make my table of knowns and unknowns, VI becomes plus 22 meters per second. VF becomes minus 18 meters per second. My time interval is 0.02 seconds, 2/100ths of a second. And A, I don't know it, but I am being asked for it, so I'm going to put A there just that I have that there. Because whatever my answer is, it has to be a relationship between all those variables. Now at this point, in a relatively simple problem, there's usually an equation we can grab. But in more complicated problems, we have to recognize the physical process, the physical issues going on here. Physically, what's happening? The ball is accelerating. The ball is changing velocity. So, do we have an equation which describes acceleration? The answer is yes, we do. Okay? So our physical principle is that the tennis ball is accelerating. Let's use the definition of acceleration to see if that solves our problem. Our definition of acceleration is average velocity equals Vf minus Vi over Tf minus Ti. Okay. Do we have an unknown on one side of the equation? Do we have nothing but knowns on the other side of the equation? Yes, we do. So our problem is now solved as far as the physics is concerned. Okay? The question is, what's the answer for our particular problem? Now, this is where another error, so the first error that you guys made is not taking into account the directions. We can get around that by drawing the diagram and make sure we assign the positive and negative directions. The second common error that occurs is you grab hold of your calculator, look at your table of knowns and unknowns, and start mashing buttons based upon the variables you have there. That's not saying you can't get it right if you do that, but the problem is if you get it wrong, you won't be able to find out where you went wrong. So your next step should be rewrite the equation with the values in it. This will also allow you to do your dimensional analysis to see whether or not you're going to get the right units. So in this case, we get meters per second and meters per second in the numerator. We've got seconds in the denominator, so our result is going to end up being in meters per second squared. Now at this point, it's totally mechanical. We can now take out the calculator and just push the buttons in the order we see on that we've written down already. Do you see? No thinking involved. Well, there is some thinking. But if you do things this way, you're going to avoid a lot of common mistakes. Otherwise, if you try to do things on the fly, take out the calculator, look at the page, and start mashing buttons, that's kind of the equivalent of trying to bake a cake by first putting the cake pan in the oven and then mixing up the batter. Do you see what I mean? Do the prep work first. It makes it a lot easier to come up with the answers. Plug in the numbers, push the buttons, and we get minus 2,000 meters per second squared. Okay? Everything makes sense now, guys? Question. How do we get the meters per second squared? Take a look in the numerator. We get negative 18 meters per second minus 22 meters per second. So meters per second adds with meters per second. We're going to divide that by seconds. So my answer is going to end up being meters per second, meters divided by seconds times seconds. You see where I'm going here? By manipulating the abbreviations for the units as algebraic variables, we end up getting the proper units. Any other questions? No? Excellent. There is another way of doing this. I can make a velocity versus time graph. If I make a velocity versus time graph, it becomes obvious what the answer is going to be. Because we see that the slope of the graph is going to give us our acceleration. What do I mean by that? We take a look at the graph. First of all, the direction comes into play. If you choose the wrong point, see, right here, there's the 22 meters per second. If you don't take the direction into account, you would choose this point right there as being 18 meters per second, but it's not. It's coming off of the wall at 18 meters per second. That means it's all the way down here. You see the difference? Okay, so another reason why you want to draw the picture. So what we see is that if we go from here down to here, that gives us the change in the velocity. In other words, the vertical change represents the change in the velocity. If we go from here across to here, then that horizontal change represents the change in time. Okay? So if we take the vertical change divided by the horizontal change, we get a slope. You following along here, guys? And thus, bold lettering. Bold lettering. Think about that. Acceleration is the slope. The average acceleration is the slope of a velocity versus time graph. So if I give you a velocity versus time graph, you can figure out the acceleration. All good? Everything makes sense? It'll make more sense when you come to the lab tomorrow. Okay? Because we'll actually do accelerations and you'll see the relationship between velocity and acceleration. Okay, great. So, if I can go from velocity and find the acceleration by using the slope, I should be able to go from the acceleration and find the change in velocity. Does that make sense? So here's my exercise for you. If an object starts with an initial velocity of 5 meters per second, what is its velocity at 2 seconds, and what is the velocity at 6 seconds? Again, work together as groups, and we'll work our way through this one, okay? Let me show you a couple things. First of all, recall that the acceleration is the slope of a position versus time graph, okay? Acceleration is the slope of a position versus time graph. And so, what I'm going to do, hello, okay. There we go. Whoops. Heck with it. Sorry, I'm playing with, you'll see what I'm talking about here in a moment. So what I'm going to do is I'm going to take that acceleration and turn it into slopes on this velocity versus time graph. Let's go back. So, whoops, excuse me. If we take a look at the first line, what is the acceleration in the first 2 seconds? 1.5 meters per second squared for 2 seconds. Okay? That means that I'm going to change my velocity by adding 1.5 meters per second each second. So, that means I'm going to have to change from here at 5 meters per second, gain 1.5 meters per second each second, and so I end up at 2 seconds at 8 meters per second. See, all we have to do is construct using the slope. All right? Now, in this, in the second part, what's the slope? -2 meters per second each second. So that means I need to draw a graph. Hello, there we go. I need to draw a graph for 1 second that goes down 2 meters per second. And then the last one was plus 1 meter per second each second, correct? So that means I got to go 1, 2, 3 seconds forward, which means I got to go 1, 2, 3 seconds up. And so that ends up here. So we end up at 8 meters per second here and 9 meters per second here. So all we got to do is use the slopes to construct our velocity graphs. Now there is another way of doing it though. The other way of doing it is looking at the areas. What I mean by that is this. Oops. I love technology, except it only does what you tell it to, not what you want it to do. Okay, so we start off with acceleration is defined as the change in velocity multiplied by the time interval. Thus, acceleration times the time interval will give us the change in velocity. On our acceleration versus time graph then, acceleration would be the height. That's the position on the y-axis, so that would be the height. Time interval is the change along the x-axis, so that would give us a base. A base times a height gives us an area. And so we can sum it up by saying that the change in velocity is the area of an acceleration versus time graph. It's not going to tell us what our final velocity is going to be. It is going to tell us what our velocity is going to change. Excuse me. Okay, we'll go over it real quick. There's our acceleration versus time graph again. The height of the acceleration versus time graph in the first segment is 1.5 meters per second. The base is 2 seconds. So what is that area going to give us? 3 what? 3 meters per second. So the first area is 3 meters per second. What is the second area? -2 meters per second, because we've got a height of -2 and a base of 1 second. So we have -2 meters per second for the second area. The third area, we have a base of 3 seconds and a height of 1 meter per second. So the area is 3 meters per second. So at the end of 2 seconds, all I've got to do is add in the first area. I start at 5 meters per second. I add 3 meters per second, and I get 8 meters per second. What about at the end of 6 meters per second? Well, then I've got to add up all of those changes in velocity. So my total change in velocity at 6 seconds is going to be 3 meters per second minus 2 meters per second plus 3 meters per second, or a net change of plus 4 meters per second. So we go from 5 plus 4 gives us 9 meters per second. There's our answer. You see? Now, is this hard? Of course not. Not when we're dealing with rectangles like this. Okay? It does get harder when you're using calculus and the curves are all really wonky and all that other stuff. But then there are techniques on how to do that. Okay? But you see where I'm going here. The area under the acceleration versus time graph is going to give us our change in velocity. And so our velocity graph looks like this. The next question is, what is the total displacement? How do I find the total displacement on a velocity versus time graph? Yes? Well, but what is it going to be? What is the displacement? How am I going to find the displacement on this graph? How far did the object move in this graph? How are we going to find it? Yes? Find the area. So what is it? Go ahead and do the calculations. Tell me what the displacement is. I call it find the area. That's all you have to do is find the area. The toughest part about finding the area is, well, how am I going to do that? Well, easy enough. Let's break it up into blocks. Let's break it up into this block here, this block here, this block here, and then we just go across like this. Why do calculus when you can do this? Yeah, well, I mean, but the point I'm trying to get at is, all you need to do is find those areas. What's the area of this first block with a height of 5 and a base of 2? 10 meters. What about this next one? 6 meters. What about this one? 18 meters. 3 in the base, 6 in the height, gives us 18 meters. Now we'll do this. So that gives us a total of 34 meters. What about on the triangles? This one here. 3 meters. This one. Nope. 1 meter. It's a height of 2 meters and a base of 1 meter. 1/2 base times height gives us 1 meter. What about this last triangle here? What is the base? 3 seconds. What is the height? 3 meters. Because this goes up to 9 meters up here. Meters per second. So it's 4.5 meters. Now that gives us 8.5 meters for that. And thus our total is 42.5 meters. That's all there is to it. That's what you guys got? Because that's how you do it. That's really all you have to do, is find the areas. Okay, so the end result is this. We've got some relationships between velocity, position, velocity, and acceleration. we see that the change in the position graph, that is the slope of the position graph, will give us the average velocity. We see that the slope of the velocity graph now gives us the average acceleration. We can turn it the other way around. That is to say, the area under the acceleration graph is going to tell us the change in velocity. And the area under the velocity graph will give us the change in position. Now, I want to ask you something very, very important. Have I said those statements before? So I am repeating the statements now. What should that be telling you? It's important. Yes, it is important. That's why I'm making this observation that I saw two people actually writing down what I was saying, as opposed to y'all should have been writing it down. But that's okay, because I guarantee you, I will be saying this stuff again. Okay? Any questions from y'all? No? Okay. Let's go ahead and call this a morning then, and I will see most of you tomorrow during the lab period.